So let's start. Let's start. Thinking. Uh, okay, so maybe some logistics first. I need to share my screen and canvas. So we will have exam on Monday. It will cover lecture 17 to half of lecture 24. Let me first show you some useful information. Oh, I send you your updated grade book. If you have any question, I just thought that some of you may find it useful before your exam. Could calm you down or stress you out a little bit, but you still have time to study. This is what March Madness season, so the athletes put everything on the field. So you should put everything on canvas on Monday. So there is modules here. Basically, the exam will be here, of course, and I think only 80 students have submitted the extra credit. It's worth 5 points. And then some of the lecture notes that we will cover today is here, including the one that we discussed last time, including jumping ring. And then the rest are just different versions of study guides. Some of you like it without answer. Some of you want it with answers. Some of you want it with a lecture. So these are the 4 different versions of the same thing that I'm willing to tolerate. Okay, because some requests could be silly, like I want the background to be blue. I don't like your font, your lab font. My font is this. I'm not gonna listen to that. Okay. In terms of the equation sheet, this is the current equations that that will be on the exam. If I think you will need more equations, I will just add them and also add the new equations in the problem. So probably you remember in previous exams, some problems they have equations right after the option, before the options. Do you want to do iClicker today? Okay, sorry. I'm just testing. If there's no iClicker, probably all of you, no. None of you will go without iClicker. Okay. iClicker. Any question? Let me okay. So there are some of you send me emails. Maybe we can start with polarization again. Is that good? No? You guys are good with polarization? So basically what you need to remember is that if you start with unpolarized light and then you introduce a polarizer, it doesn't have to be vertical. But basically what a polarizer do to an unpolarized light is it cut the intensity by a factor of 1/2. Okay. And then next is just what you need to keep track is the angle between the incoming beam or incoming electromagnetic wave and the polarization axis or plane of a polarizer. Okay. Or in your textbooks, they call it analyzer, but it's basically polarizer. I think polarizer is here. And then the equation that you use is Malus law. If you're curious, it's because the intensity, we know that the intensity is proportional to the strength of the electric fields. Or if you want to be more exact, okay, square divided by 2 to make it something like this. Okay. Then the reason why we get cosine square of, I need to change this to phi, is because it's the projection of the incoming beam to the axis, the polarization axis of the polarizer. Okay. This is why we get cosine square. So as long as you keep track whether the input of a polarizer is polarized or not, and understand the angle between the polarized the incoming polarized beam and the angle of the polarizer, you should be good. And make sure you know how to use your calculator. Any other question? Yeah, Dinesh. Okay, good. Thank you. That means I wasn't being clear. Okay, you guys need to pay attention, okay? This is important because I guarantee that I will put this question on the exam. Of course, it's only a fraction of a problem. If the incoming beam is unpolarized, then the intensity after a polarizer is 1/2. This is because, you know this. I don't think I need to do this again because you guys are probably tired of seeing this left angle bracket cosine square phi, right angle bracket. This one is mathematically, this is the reason. This is the reason why we get a factor of 1/2. And then if the incoming beam is non-polarized, then you can use Malus law. Any other question? There is this question from one of your classmates, from Sarah. So the question is about magnetic energy density. Okay, what is a magnetic energy density? What is the symbol? U. Yeah, U. I don't know. Yes, U. The symbol is small u. Okay, like this one, this small u here, U. Okay, and there is a subscript B because it's magnetic. And then the equation is 1/2 B square over mu naught. And you can of course write it different way, and I don't need to do this, something like this. They're basically identical. And after this, all you need to do is putting the number or the numbers. Well, there is only one number, but this is actually from Pearson. And I will do my best to avoid this kind of problem because I like all the units to be in SI. But in terms of the units, 1 meter is equal to 100 centimeter, right? You know this. Do you know that or no? And then so 1 centimeter is 10 to the minus. Okay. So as long as you know that, then you should be good. And then 1 meter cube is equal to 100 cube centimeter. So it's 10 to the, so basically a million centimeter. So similarly, 1 centimeter cubic is equal to 10 to the minus 6 meter cube. So, and then all you need to do is putting this number and this number, and you should get the answer. You want to try this or no? Or do you think it's not a good use of your time? Okay, so let's spend 2 minutes on this, okay? So I'm gonna send this to iClicker. So 2 minutes. Okay, so almost all of you have answered. Okay, like 40 more seconds. While waiting for 40 seconds, I can probably do that in front of you. Tesla square 2 times. All right, time is up. So what is the answer? I think I shouldn't. Do you want me to continue or no? No. Okay. So okay. So I'm not gonna. Basically, this one is roughly 1.92 times. Did that this morning. Times 10 to the 8th joule per meter square. Oops. Meter cube. And then, you know what? Let's make it cleaner. Meter cube. And then you just do 1 meter cube equal to 1,000,000 centimeter cube. Then this one becomes 2. Okay, so you get basically 1.92 times 10 to the, or 192 joule per centimeter cube, which is not exactly what you have, but it's close to option A. Good. So what else that we should discuss? There is this problem in the in lecture 19 or so, 20 maybe. Eva asked this question. Are you still working on this? So this is another. So the previous one was from Pearson. I don't quite like it because of the unit. This one I don't like it because of the 3D representation. But I think you can do it. Let me use my Apple Pencil. Maybe it's easier. So first, the question is: there are two solenoids in the figure above. They are basically coaxial and very close to each other. The question is, while the resistance of the variable resistor in the left-hand solenoid is increased in left solenoid at a constant rate, the induced current through the resistor R will, okay. So First, this is not the first time that you encounter variable resistor. Variable resistor is basically a resistor that has that you can change its resistance. Like volume knob is one of them. You can increase or decrease volume by rotating a rotary knob in the old days. Right now, you just punch number or move your mouse, but in the old days, there is a rotary knob that you can rotate. Second, you need to know right-hand rules, and all of you should know that the direction of the current is the direction of, or is the way you curl your fingers of your right hands. Don't use your left hands. Okay. And then the direction of the magnetic fields or flux is the direction of your finger. So first you need to know right-hand rule. I don't know what this thing is. Something like this. And then you need to know flux. What is flux? What is a magnetic flux? One of you. What is a magnetic flux? Mitchell. Is there Mitchell here? No? Just my imaginary. It's B times A, the magnetic field times area times cosine angle. Okay. And then next, you need to know Lenz's law. And you need to know, first you need to know, you need to know Ohm's law. Basically, V is equal to I times R, okay? So for a system with a constant voltage, and we can vary the resistor, let's say, using a variable resistor. This is a variable resistor. Then V stays the same. That means if you increase R, so that's what is given by the problem, you increase the resistance. If you increase the resistance, this will result in decreasing what? I. V stays constant. So basically, the left, back to this figure, the left coil will produce magnetic field that points to the left. This is the direction of your thumb. So by using the right-hand rule, we know the direction of the magnetic fields. And so this is the direction of the magnetic fields, and we know the direction of flux. Is that clear so far? And then what is next? Next, we need to know whether the flux increases or decreases. So if we decrease the resistance, the current will decrease. So B here is actually mu naught N divided by L times I. So if we increase the resistance, the current will decrease, and B will decrease, and flux will also decrease. And the flux still points to the left. It decreases. Okay. So what will the right solenoid do? That's the question. It will produce currents. It will produce magnetic field. Holden is correct. To minimize the change. So if the flux is smaller and smaller, the other coil wants to add flux to keep it at the same level as before. So I'm gonna use, I don't know, different color. So this is the induced magnetic field. Okay. And because the second coil has its own resistance, then there is a current. The current is equal to, so first the induced EMF is equal to minus N, the change of flux over time. And then the current is simply, you can write it explicitly, it's fine. Okay, so that's the current. So the question is whether the currents flow from A to B or B to A. What is the answer? What? Who said A to B? Let's do a clicker so you get points. Sorry. that's the option. So either A to B or B to A. Okay. Let me make it slightly bigger. Let's not spend too much time on this because I think all of you get it. Okay. So basically, all of you have answered 5 more seconds. Well, I can show it to you. So it's, okay, so when the distribution is equal, it's time to pause and go through the problem again. Right now it's not equal, so maybe we should skip the explanation. So do you want me to go through it again with you or no? Yeah. But it's not a uniform distribution. Okay, let's stop. So the answer is, I think B, let's say. Okay. So you don't have to use your right hand rules, etc. Basically, what you need to realize from this figure is actually better than the other figures, the other similar figures in your textbook. I can easily follow the right hand, the orientation of the wire or wires. If you know that these two solenoids are identical, okay, and the flux decreases, that means the direction of the current should be the same as the other one, because you want to produce the same flux, not the magnitude, but the direction. So the current should flow from B to A, similar because the other solenoid also, the current flows from right to left, okay? So on the exam, if you see similar problem, I may change the questions. You know, I may say decreasing resistance. Then don't just answer B. Okay, is that clear or no? Yeah. Yeah. If it's decreasing, that means okay. That's a good question actually. How to do this? Clear page. Okay, so if it's decreasing, the flux still points the same way, but it's increasing, right? It's increasing. So what the other coil wants to do is it wants to minimize the change of the flux. So it will oppose the change by making or by getting induced by, so nature says that nature will induce magnetic fields on the second solenoid that points the opposite direction, because the one that initiate the dynamics, the flux increase. Is that clear? Any question? So, so this is, if I break it down, this is how I like to think about the problem, and you will have enough time. Most people spend far less than 60 minutes in the previous exam. So you can read the question carefully and make drawings. Oh, some announcement. Ross will have a review session today. He is my best TA this semester, and my worst TA at the same time. Yeah. Okay, good. So yeah, this type of problems involve like 3D visualization. I'm not going to promise anything, but this is, I can honestly say that I don't like this type of problem because of it doesn't really test these four concepts here. It also tests you, tests how well you can interpret a figure, which is not the most important skill set from this class. Okay. Yeah, Hannah. Slide with answers, or so this one. Let me switch to this one. No, wait, what is the number of the slide? What is the slide number? This is the latest version, or? Okay, 247. This one? Which one? Maybe I change, oh, this one. Ah, I see. Okay. This is something that we cover really fast in the class. Thank you. And I may, if it appears on the exam, I will add one more equation. So let's use this formula here. And let's take a step back. Let's have a more like a broader view. So flux is equal to B times A times, is there a way to make it bigger? Maybe like this. Okay. B times A times cosine phi. And this one is phi, small phi, big phi. Okay. And phi is the angle between the normal vector that is perpendicular from the plane of the loop and the magnetic field. And change in flux, basically, so this is change in flux over time, leads to induced EMF, right? Or we can even do it exactly. And there are different ways to change flux. How to change a magnetic flux? Let's say you have a constant magnetic field. So one way to change flux is, this is a classic problem in many textbooks, similar to experiment by Orsted. So let's say and let's make it more interesting. Loop doesn't have to be a rectangle. Let's say we have a ring like this. How to change the flux? So this one, we know that this long wire will generate a magnetic field. That points towards you and towards above the wire, and points towards the whiteboard below the wire. And I will get to the answer of your question, Sam. So how to change the flux here? How to change this? One is you can vary the current. So in the exam, I may choose that route. One, the ring can move up, or the ring can move up. Sorry. Or the ring can move down. Okay. So the reason why I changed you will see why I changed the position of the ring. So first, notice that this one, the magnetic field of a wire is, I think, mu naught I. This is using Ampere's law, where R is the distance between the wire and the point of interest. Then further from the wire, the magnetic field will be less, right? So if we move the wire perpendicular, so either you can also move the wire, of course, you can move the ring. If you move the ring away, then the flux will decrease. But if you move the ring closer to the wire, then the flux will increase. Okay? And this is a common problem in many textbooks. How about if I move the wire exactly parallel with respect to the wire? No change, right? So this one, flux stays the same. Good. So for AC generator, so first, any questions on this? This appeared in last year's exam. I think I used, did I? I don't remember. I also wrote, I put ring exactly in the on top of the wire. Anyway, it may or may not appear in Monday's exam. All right, but for AC generator, the ring actually rotates. So this you can also rotate the ring, and you get basically the math is the same, but the physics, of course, meaning like the physical realization is different, but the math is the same. So for AC generator only and other rotating system, AC generator, flux is equal to, for AC generator or electric generator, B times A times cosine, I hate this Greek letter, cosine small phi. And if we rotate at a constant speed, at a constant rotational speed or angular speed, what is the symbol of angular speed? What is yeah, little omega. Okay. And what is this equal to? 1 is equal to V divided by R, but that thing is not useful. We don't really need R and V here. It's equal to 2 pi divided by T, where T is the period of the rotation, and 1 over T is equal to frequency. So this is here. So omega is equal to 2 pi F. So I don't expect you to memorize this, so I will give you the equation. If that thing doesn't appear on the equation sheet, it will appear basically in the same problem. Okay. I'm sorry that I have to say the same thing over and over again, but you'll be amazed with the number of emails that I received that ask the same question, including whether we use Canvas gradebook. The answer is no. Okay. All right. So, and then the change of flux divided by time. It turns out that you can do derivation, but to save you time, this one is B times A times cosine omega t. So if it rotates at a constant speed, the angle is just omega times time. Okay. So because in the interest of time, I'll just show you the formula for AC generator for the change of flux over time. So you have the angular speed here times BA. Instead of cosine, you use sine. Okay. And for this problem, I just define this one as EMF maximum because this function here oscillate from omega BA to minus omega BA sine. So in the end, that's what we need for one loop, because I just made a mistake. For more than one loop, what is it good? For more than one loop, you just add all of them. So you add n to all of them, including here. So WNBA, that's Emax. So Emax is omega n B A. And in this problem, the area is given. N is 200 turns. The E, basically, Emax, AC generator with a maximum EMF of 8 volts. So this one is 8 volt. So to solve this problem, omega is equal to 2 pi f. So this one is 2 pi f times NBA. Sorry, yeah, NBA. So F is basically E max divided by 2 pi N, 2 pi NBA. Good. And it's on the study guide, so you don't have to take notes. But I remember that in class, we didn't do this, or I did it very fast. But it's on the study guide. If you're interested in the derivation, you can talk to me after class. Yes, Sophia. Oh, good question. I can give you this and this. I think this one is given already. It's here, right? And I may add okay. What time is it now? 10 more minutes. Any other question? I think Hannah asked about radiation pressure. Just remember, for radiation pressure, it's a conditional equation, meaning for perfect absorber, it's I divided by C. Maybe I did it here. Sorry. And I know some of you print the study guide, but I encourage you to download the latest version, because when some of your friends ask me question, I sometimes do the problem on LaTeX, meaning like on the PowerPoint. I don't use, basically on PowerPoints. I don't use PowerPoints, but on the slides. So that thing is expanding because of the emails from your classmates. Where is the, sorry, there is radiation pressure question. Yeah. So for radiation question, remember pressure has two equations. We call this conditional equation. Case one for perfect absorber, because again, light hits and stop. So delta V, the change of momentum is V minus 0. But for perfect reflector, light hits and then bounce without loss of speed. So the change of speed, which is proportional to change of momentum, is V minus V. So it's 2V. This is why we get a factor of 2. And then you know this, and I will give the equation if you need it. F is equal to pressure times area. And then you should know F is equal to M times A, right? F is equal to MA. I don't remember here. F is equal to MA. You should know that. And I will not give, like cosine 45 degrees because you have calculator. Any other question? Let me think. What is? And then we discuss the type of waves. There is one longitudinal, one is transverse. You should know that. Yeah, Sophia. Okay. Do you find it confusing, or those are the type of questions, the level of difficulty, I would say like 75% of the maximum level of difficulty. I know that thing is subjective. This is the type of thing that may appear on the exam. Of course, I will start the exam by easy question to build your confidence, but this is towards the end to keep you entertained. Okay, so basically here, okay, the question is, I shouldn't show you this, okay. On a computer chip, two conducting strips carry charge from P to Q. P is here, Q is here, okay? And from R to S. So there are two wires. So you just need to keep track which one is which. I took this from a different textbook. I didn't write this one. I may, if it appears on the exam, I will change the color. So one is red, the other one is blue, let's say. If the current direction is reversed in both wires, the net magnetic force of strip 1 on strip 2 is, so we know, so you need to use right-hand rule in many orientation, of course. And then basically, if the field points towards each other, you get repulsion. If the field points towards the same direction, then you get attraction. One way to remember is, I like to think sometimes in the context of permanent magnets or bar magnets. We know that the magnetic field points towards the South Pole and away from North Pole, and we know these two attract. So you have seen the answer of this problem, which is A. So I'm not gonna, and we only have 4 more minutes. So basically here, because you reverse the direction of the currents, then you flip the direction of the magnetic fields. But since you reverse the direction of the currents, which in turn reverse the correction, the direction of the magnetic field due to the current on wire P, wire 1 or 2. Since you flip both of them, then it will remain the same. Meaning, I mean, this is the analog, not the perfect analog, but it's almost like you flip these two permanent magnets and you still get the same attraction or repulsion. Does it make sense? I'm just simplify the problem for you. Yes, you. Yeah. Oh, okay. Like number one. Physics 112 is number one. Okay. If no other question, one more announcement. There is an awesome, I know some of you are in SMS. There is like one of the best scientists in my field will give a talk at 3. Typically no one show up from my class. But if I see you in the class, you should, I will be thrilled. I met him yesterday and I was blown away. He's brilliant. His name is Kendall. The announcement is on SMS website. All right, so good luck on your exam 3. I'll see you on Wednesday. Yeah. Oh, yeah, you can put it there. Thank you.